Okay, last time we finished with nomenclature. Now we're going to talk about aqueous solutions, solubility. You can see these are all the topics that basically covers everything for solutions until we start talking about acids and bases. We'll go over net ionics, complete ionics, solution concentrations, so molarity, the dilution equation, which is hard not to call the dilution equation a trap because it's a trap because you're going to want to use it when you shouldn't use it. And then solution stoichiometry, which is where dilution often gets used incorrectly. Okay, so consider two familiar aqueous solutions, salt water or sugar water. In both cases, you got a homogeneous mixture. One's got sodium chloride and water, the other one's sugar and water. And when those things completely dissolve, they seem to disappear. You guys probably noticed this too. Actually, wait, no, maybe I'm thinking of Chem 20. If you took Chem 20 and you did the separation of a mixture lab, there's this one part where you've got a salt water solution and you're supposed to boil it until a solid appears. And it boils for a while, and then inevitably people come up and ask me, and they're like, the water's almost gone, where's the solid? But the solid comes out as soon as it's not soluble in the water anymore because there's so little water. So a lot of times salts, not just NaCl, but other ionic compounds, or sugar, even molecular compounds that are soluble in water, they don't evaporate with the water, or they don't boil away with the water, they get left behind. And in fact, if you do this with just tap water, you'll find that there's salts and things in that also, especially around here. And especially if you have a well. So if your house gets well water, that's going to be very high in dissolved solids. So how does this even happen? It's different for sugar and for salt. At the core of it, basically have a tug of war between different intermolecular forces, which we'll talk more about later, but these attractive forces between the solvent, which is the bulk of the solution. In this case, if we're talking about sugar water or salt water, it's the water. And we've got the solute, which is the thing that the water is trying to dissolve. And so the solvent-solute interaction is one attractive force, but there's also solute interactions that the solute is trying to stain with other solute particles. And these two forces are working against each other. You also have solvent. So if the solvent-solute interaction is strong enough, and it can overcome the solute-solute interactions, then it will start to pull apart the solute and surround it in the solution. And so when we talk about something being soluble in water, really what we're talking about is that its intermolecular forces of the solute are weaker than that of the water in the solute. And usually that only extends up to a certain point. You can only dissolve a certain amount of something. So part of this comes from, at least for water, the fact that it's a polar molecule. And the distribution of electrons means that on the oxygen side, this is the oxygen side, these are hydrogens. The oxygen has more of the electrons surrounding it than the hydrogens do. And it essentially has more of its fair share. And that creates this partial positive. So the delta, I should say this is delta, this is a lowercase delta. That symbol means partial. So it's not a full positive charge, but it's a partial positive charge. And then on the other side, so for the water, we have a partial negative, and then on the hydrogen side, we have a partial positive. So we have essentially two poles, a positive pole and a negative pole, just like a north pole, south pole on a magnet. And we'd say this has a dipole. So we got two sides. So for sodium chloride, the primary effect here is that the negative side of the water is attracted to the positively charged sodium. And the positive side of the water is attracted to the negatively charged chlorine or chloride. And in water solution, that solvent-solute interaction is stronger than the solute interaction, and the water will start to pull apart any sodium chloride crystals that are in the water. And then once it gets that positively charged particle off or the negatively charged particle off, it goes ahead and it surrounds them. So each ion will attract several water molecules. And they'll form basically bubbles around each of the charges. And each of these water bubbles will have, right, around the positively charged sodium, the negatively charged sides of the water will be on the inside. And then you'll get positively charged on the outside. And then it'll be the opposite for the water around the chlorides. Once it gets pulled off of the crystal, there's no way that it can find its way back to, so like the chloride can't find its way back to another positively charged ion to reform the crystal because there's too many water molecules surrounding it. Which is why if you start to boil this, you start to remove water from the solution, there are fewer and fewer water molecules. These sort of bubbles around each of the ions starts to break apart and they start to recrystallize. We'll mention this at the end too, but because we've got these positively and negatively charged ions, and again, the inverse charge, or I guess matching charge on the outside of the water, it's able to conduct electricity through the water because you've got free-flowing charges. All right, so for representing aqueous reactions, which are going to be by far the most common reactions that we cover, most of these are aqueous. That's what the AQ means. Sometimes we'll have solids, but this sort of representation of the chemical reaction is a little bit fake because it's giving us these compounds, which in an aqueous solution don't really exist as compounds. We just saw with the sodium chloride. Once the sodium chloride goes into the water, it's not sodium chloride formula units. It's independent sodium ions and chloride ions surrounded by water in the solution. And that's going to happen for any ionic compound that's soluble in water. So which of these are soluble in water? Yeah, KOH, MgNO3, and KNO3. The only one that's not is the magnesium hydroxide. So this S means that it's a solid, which means it did not dissolve. So anything that's aqueous is going to be soluble in water. And all of those will exist as separate ions, not as formula units or as crystals of that compound. Now, most of the time when we're writing a molecular equation, the reason we want the molecular equation is to just see all of the components in the most compact format possible. And the aqueous part of this tells us that these are existing because they're ionic compounds, because it's only ionic compounds when they're aqueous that are dissolved and dissociate into ions. Sorry, that's what tells us that we should think of them as separate ions. But the complete ionic equation is the one that shows us all of the species as they actually are in a solution. So we'll separate all of our ions. And then we can talk about the net ionic equation, which shows only the species that actually change. Only species that have bonds that break or bonds that form. So for the complete ionic equations, basically any soluble salts, so any salts that are aqueous, or you'll look up on a solubility chart, strong acids and strong bases will all exist as ions. Insoluble substances, and this includes, and this is where we are starting to move past Chem 20, more into Chem 1, truly Chem 1 stuff, right? Weak electrolytes and then non-electrolytes are written as molecules. So we do not separate those into their ions. And also, actually, let me highlight these in a different color. Let's do green. So weak electrolytes, non-electrolytes, solids, liquids, and gases, those are the easy ones. You need to know what a weak electrolyte is or what non-electrolytes are, but those will all be written in molecular form. So we don't separate them. So in this equation, can't really zoom it in that much because it's so wide. And this is part of why we don't use net or complete ionic equations for everything, because this is more compact. But you can see here, lead nitrate is lead and two nitrates. And so we get one lead, we get two nitrates. That separates out into those ions. Same thing, the two applies to the potassium and the chloride, so it's two potassium ions, two chloride ions. Lead chloride is insoluble, it's a solid. And then the potassium nitrate, two potassiums, two nitrates. So if you're starting with a molecular equation that's already balanced, those coefficients carry on into the complete ionic equation. Now for the net ionic equation, we only care about the things that are actually reacting. And so the fastest way to identify what's actually reacting is to look at the things that aren't ions. So the lead chloride solid, not an ion. So that means that the chloride from our reactants and the lead from our reactants are the only things that actually reacted. The other way you could think of this is to look at, let's use orange, look at all of the things that stay the same. So the nitrate stays nitrate. Potassium stays potassium. And so those reactants, those products, didn't change over the course of the reaction. So for our net ionic equation, you can think of this similar to a math equation, right? It's the same thing on both sides, so they cancel out. And our net ionic equation can then just boil down to lead plus chloride gives me lead chloride. The net ionic equation, again, is our, let me go back up to this. The complete ionic equation, sorry, is the truest form of what's actually happening in the solution, because lead chloride and the lead chloride are not the only things in the mix. There are other things around, and that can become relevant if you do more than one step to a reaction. If I add something that reacts with the potassium or reacts with the nitrate, then that could change the outcome of the next reaction. Whereas the net ionic equation is the simplest look at what is actually happening in terms of reactions. Otherwise, these spectator ions are just floating around. Okay. So consider this following reaction in an aqueous solution. What species, so we say species refers to any of the compounds in the solution. Which species is not going to separate into ions? H2O, because it's a liquid. So we're going to leave H2O alone. And then for the rest of these, this will be 2H plus aqueous plus 2I minus aqueous. Barium. 2 hydroxides. Water stays together. And then 2I minus. Oh, forgot this one. Now remember, when doing these types of problems, remember you can take if you have a blank piece of paper, turn it landscape so you have the entire width, long length of the paper to write these instead of trying to fit it into the shorter width. Okay, so that's the complete ionic equation. Any questions about the complete ionic equation? Is everybody with me on how, right, my hydroxides from barium hydroxide turn into 2 hydroxides? Good. Okay.
Wait, no, do it.
Do it again. Why did it do that?
I was spacing out the whole time. I was looking at it, but I think I was just.
I know that feeling. I know that feeling. It's like, cool, I just looked at all of those words and I remembered nothing.
It's like you look away for 1 second.
We said this is the only thing that's going to stay the same. So I basically just, when I got to that, I just rewrote it. For everything else, you separate it out into all of the ions. So that means that the hydroxides here, and actually, if we go all the way to the first one, 2 HI. So right, there's 2 hydrogens, there's 2 iodides there. So that's 2 hydrides, not really hydrides. 2 hydrogens, 2 iodides. So that's from that. And then for barium, there's only 1 barium in that, but there's 2 hydroxides. So instead of writing this in parentheses with the 2 out here, I make that 2 the coefficient instead of a subscript. And then that was the end of our reactants. So move over to products. The water stays the same. And then for barium, same kind of thing. We're 1 barium, so 1 barium. Subscript 2 for iodide means 2I minus. All right, so now that's the complete ionic equation. Yes. Oh, yeah. You definitely need the charges. Somebody told me that Alex wants you to put the sign before the magnitude on Alex. It wants +2 instead of 2 plus. So I haven't yet, but I'm going to email them about that because they're wrong. I've done that before. Although one time I emailed them and I was like, you're wrong. And they said, no, we're not. And then I said, yes, you are. And I explained it thoroughly. Cool, that's in the recording now. So how do we go from the complete ionic to the net ionic? Cancel out the stuff that's the same on both sides. So what's the same? Iodides, bariums. Yeah, that's it. So then we can rewrite this. It's 2H plus aqueous plus 2 OH minus aqueous 2H2O liquid. There aren't many things that will just be liquids. Just one more thing I should do.
If say in a word problem, it's even like a word problem, how do you tell which equation to put in?
Yeah, so if you're given a word problem, how can you tell what's going to be aqueous and what's going to be solid or what's going to be liquid? Most of the time, so the one liquid you should always know is water. If there's water, it's a liquid always. Unless it says water, vapor, or gaseous water. If it doesn't tell you that it's something else, then it's a liquid. Aside from,
Well, if it's a gas, then we're still gonna treat it the same thing.
if it's a gas, yeah, then it'll probably tell you that it's a gas. For the other things, like whether or not they're aqueous, we haven't gotten to solubility rules yet. I might need to look and see what the other professors are doing in terms of solubility rules. I generally don't think it's a thing to memorize. There are some things that you should memorize about solubility rules, but otherwise most of the time you just use a table. But you would look at your solubility rules, and actually this previous example was a good one. So like lead chlorides is something that you could know from a solubility table. That's insoluble in water. And that's a pretty common one. Yeah, so either solubility rules or it'll tell you solid lead chloride. Okay, so there's one more thing I need to do here for my net ionic though. And get rid of the coefficients. They're all 2. Right, so I can simplify this to not have those. And actually, maybe I should have waited. So that would be the net ionic. Does anybody remember what type of reaction this is? Oh, okay, yeah, it is a synthesis reaction. Got 2 things coming together to make a new thing. One new thing. It is not a double displacement. Sorry, I was looking to see if it is a redox. Nope, it's not a redox. Yeah, acid-base neutralization reactions. So these will come up again later, but in an acid-base neutralization reaction, you always end up with the same net ionic equation. I think it's like the next section we're going to cover. Not today. So those are complete ionics, net ionics. When we're talking about solution concentrations, this is not concentration as in like focus. It's concentration as in how much of the salt or dissolved thing is there in the solution. And usually we normalize that to some amount of solution. The unit that we'll use the most is molarity. But we can have, because they're mixtures, we can have different amounts of the solute or the thing that's dissolved. So typically the solvent is present in the greater amount. When the solvent, or I guess when water is involved, it's almost always the solvent, except for rare cases. Then the solute is present in lesser amounts. And you could have more than one solute in a solution. The net ionic equation, we just had a whole bunch of different solutes. And the amount of the solute is variable. There are some things where, at least by mass, you can dissolve more mass of like high fructose corn syrup. The reason that's used in all kinds of sodas and sugary drinks is because it's crazy soluble in water. You can fit more than 100 grams of high fructose corn syrup in 100 grams of water. Water would still be considered the solvent there. All right, so water is, an aqueous solution is one where the water is the solvent. Sometimes even when it's not the highest mass. So I guess in vague, broad terms, we can talk about dilute solutions and concentrated solutions. So something that's dilute means there's a lot of water and a relatively small amount of solute. So not very much dissolved in it. You might consider like tap water around here to be a very dilute solution of like magnesium and calcium. Concentrated solutions have a large amount of solute compared to the solvent. So those are like the very qualitative definitions of concentration. But we're going to be, of course, way more specific most of the time. And the best unit for chemistry in solution concentration is molarity, a quantitative definition of concentration. So molarity is the amount of solute in moles divided by the volume of solution in liters. So it's the volume, of the solution, not of the solvent. Right, the solution, it's the solute, and I'm not going to, actually, I probably shouldn't put plus here. It's the solute and the solvent. So those two things combined. So the volume of the whole solution together goes on the denominator. My advice to you for any of these problems is when a problem gives you a concentration in molarity, just convert it straight to moles per liter. Because when it's in molarity, it hides the fact that it's made up of 2 units, moles and liters. And when you have something that's made up of 2 units, you can use that as a conversion factor. So if I know the volume of a solution and I know the molarity, I can calculate the number of moles of that thing in the solution. Or if I have the number of moles and I have the volume, I can calculate molarity, or I can calculate the volume. And basically all the time we're using this as a conversion factor. When you're preparing a solution of a specified concentration, the way you do this is you will take, this is called a volumetric flask. It's called volumetric because it very specifically will measure out 1 volume of solution as long as you fill it up to the 1 liter mark in this case, or whatever it is on that solution, right? Unlike a graduated cylinder or a burette or something, those measure out variable amounts of solution. This does 1. Like this one would only do 1 liter. And the reason they have this really long neck on them is because it makes it a lot easier to measure or to get like just a little bit. And it makes your volumes more accurate. So the long neck also though, and I don't think you even have to make any of these in this class, like specific concentration solutions. But you always want to add the thing that you're dissolving or put a little bit of water in here first, then add your solute if it's a solid. Then you mix it. Because once you fill this up, it does not mix. You'd have to either spin the whole thing or you have to invert it. So you can put a stopper on the top and you can flip it over, and then the gas bubble or the air bubble will go to the bottom and back to the top. And you have to do that something like 50 times and then rotate it every time to actually get that solution to mix. We've done it before and it takes forever. So because of that, you really want to get it well mixed before you top it off. Yeah, because it's crazy how little the water will move. The other thing is, when you add and you make solutions like this, depending on the thing that you're dissolving, it will change the volume of the solution a little bit. So if I filled this all the way up to with 1 liter of water, and then I put all the sodium chloride in there, once it gets dissolved, I actually don't remember how sodium chloride specifically affects. The volume might be a little lower or it might be a little higher, all depending on how that solute interacts with the water. So you want to mix it and then top it off. Okay, so how many moles of solute are required to make 3 liters of a 2 molar solution? What is molarity? moles per liter. 2 molar would be 2.0 moles per 1 liter. But I want 3 liters, right? So if I take 3.0 liters times 2.0 moles per liter, liters cancels, 6.0 moles. If you have to, you should write down somewhere, molarity equals moles per liter. We'll do some more of these. All right, so calculate the molarity of a solution made by adding 45.4 grams of NaNO3, sodium nitrate, to a flask and dissolving it with water to create a total volume of 2.5 liters. So this is calculate the molarity. What is molarity? Moles per liter. So we want to know moles per liter. It's always moles per 1 liter. In this case, it's going to be moles of NaNO3 in 1 liter per 1 liter of solution. So what do we need to do? Grams to moles, right? It gave us grams, but for molarity, we need moles. So 45.4 grams NO. Oops. Sodium's 22.99. That's the wrong button. Plus 3 times 16. We can do it this way. 85.00 grams, 1 mole. So 45.4 divided by 0.534117647, and that's moles. Okay, so now I have moles and I have liters. And what's molarity? Moles divided by liters. So you take the moles of sodium nitrate, never rounding, divided by 2.50 liters. That's going to be 21. Now we round 4. What happens to the 2.5 liters of the denominator? Becomes 1. So when I divide these, because I've got 2 different units, the units don't cancel, the units don't interact. But if I divide this by this, that's going to tell me the number of moles per one of whatever's in the denominator. In this case, liters. So this is 1 liter. And now, just to finish this off, we might say, oh, that's 0.214 molar. Run out of space. NaNO3. Okay. Any questions? Do you guys remember molarity? Vaguely. Okay, calculations, basically, like this question, actually, let me back up again. This question asks us to find molarity. So we need to start with basically the concept that molarity is moles per liter. Say, oh, I've got grams of this, I've got liters of solution. So convert grams to moles divided by liters, that's molarity. So we're finding molarity in that case. Just as often, perhaps more often, we're going to be using molarity in this form where it's the 0.214 moles per 1 liter, and use that to convert between either volumes of solution, so for example, liters to moles, or we could say moles and convert it into how many liters of solution we need to get or have to have that many moles of whatever we're starting with, so NaCl in this case. So we might say, yeah, so we could translate this to liters of solution to moles of NaCl. The questions that answers, or the question that's being asked is, I'm just going to use X. X liters of solution contains how many moles of NaCl? So you're given the X, you calculate how many moles it is. This other one would be like X moles of NaCl would be contained in how many liters of solution. I'm saying I want 10 moles of NaCl. How many liters of this solution do I need to have that many moles total? I'll probably be doing the top one more often. Okay. How many grams of sucrose are in 1.55 liters of 0.758 moles or molar sucrose solution? What is molarity? Liters. Moles over liters. Should become your mantra for solution problems. What is molarity? It is moles over liters. You guys know the one about what did the monk order from the hot dog stand? He ordered one with everything. Mantras. Okay, so this is moles per liter. So rewrite it as 0.785 moles per 1 liter. And we're asked for grams of sucrose. So if we have the chemical formula, we can always convert between moles and grams. And now I have a conversion factor here, 0.758 moles per liter. And my starting number, or the other number I'm given, is 1.55 liters. So I can convert 1.55 liters into moles, and then use the chemical formula to find grams. So we start with 1.55 liters of the solution. It's 0.758 moles per 1 liter. That will calculate the moles, and then molar mass of sucrose is 342.34 grams per 1 mole. Or correct sig figs. So molarity is just a conversion factor, converting between liters and moles. And questions? Okay. Here, I'll give you some time to do this one. Oh, I guess this is a slightly different problem than I thought it was. That's fine. So if you dissolve 25 grams of salt, 251 grams of water, what would the mass of that solution be? Yeah, because you see that salt go in and it disappears, but it's still there. So even though something dissolves, the mass is still there and doesn't go away, so it just adds to it. So it'll be just 25 plus 251, 276.
So it wasn't a trick question. It was just straightforward. Okay.
The trick was how straightforward it was.
It's like it's too straightforward. You're like, is this a trick?
Can it be that? Woohoo! So yeah, sometimes overthinking it makes it way harder. Yeah, the trick here is that you don't normally think of even solutions as by their mass. It's like a volume. Or when you add something to it, you don't really think about how that adds to the mass of it. But if I put 100 grams of fructose into 100 grams of water, I would have a solution that now weighs 200 grams. And then again, the way that volume changes when you mix things is weird and depends on the things you're mixing. But the mass is all there, right? Matter, mass, neither created nor destroyed. Conserved. Okay, so if we've got solutions of different concentrations, or if we've got a stock solution, and the reason we talk about this as its own topic is because it's way easier to ship and store solutions in a more concentrated form. So this is why you can go to AutoZone or whatever and buy antifreeze. They'll have ones that are pre-mixed, or they'll have the concentrated stuff. Or you can get a lot of cleaners in a concentrated form. You don't want to use it in the concentrated form, but you can take that one thing and then make gallons upon gallons of cleaning solution at the right concentration from a small bottle. Question.
I wanted pre-mixed Starbucks coffee, and he bought one, and it's concentrated Starbucks coffee.
You just add water?
Just add water. I'm like, that could be kind of dangerous. Not reading.
You got, yeah, pre-mixed Starbucks drinks and you just have to add water. Yeah, you might just drink the straight Starbucks drink. Concentrated. I'm sure. Did you taste it? It probably tastes awful because it's just too concentrated. That's what, like, instant coffee is coffee where they've just taken all of the water out. And it leaves behind all of the other stuff that makes coffee. So you add hot water and you get something similar to coffee. Because it's not exactly a one-to-one. Okay, concentrated solutions just means that there's a high concentration of whatever the solute is, or solutes, in the case of something like antifreeze or concentrated Starbucks coffee. And the key is that most of the time we want lower concentrations. And so to dilute something, we add water to it. And the trick to this solution dilution equation is that the moles in is equal to the moles out. The only thing that changes is the volume. So really what we're doing when we're doing one of these is we're saying, okay, I want a solution that has this many moles per liter, some molarity here, and I want X amount of it, maybe 100 milliliters, maybe I want a full liter of it. And the question that you're asking is, how many moles do I need to put into my 1 liter of solution to get the concentration that I want? So you got to calculate the moles in to get your moles out. But since it's coming from another solution, we calculate the moles based on the molarity and the volume of that concentrated solution. See if we could do this so it makes a little more sense practically. Oh, here's an example of a dilution of a solution. So we got a 10 molar stock solution. Oh, calcium chloride. So you got 10 molar calcium chloride, and they take 150 milliliters, 0.15 liters of it, and add it to this 3-liter flask. This is a 3-liter flask. I'm going to zoom in on the calculation on the bottom here. Because the desired concentration is going to be 0.5 moles per liter. So what you do is you say, I've got a 3-liter flask, I want 3 liters of the solution. I want a concentration of 0.5 moles per liter. That means I need to get 1.5 moles of calcium chloride. Now that's coming from another solution. So you say, if I want 1.5 moles, then how many liters of this solution, 10 molar solution, do I need to add? And it ends up being 10 divided, what is it, 10 divided by 0.15? No, 10 times 0.15. And that also equals 0.15 moles. So we're just calculating, how do I get 1.5 moles of this solution? Because I want 1.5 moles of this solution. feel like that was about as clear as mud with the numbers already in there. So let's do calculation. Ah, yes. So to what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.75 molar calcium chloride solution? Just thinking, I want to rephrase this so that we're thinking about it in terms of moles, but this question is asked not in that way at all. So in this situation, we're starting with, if we ignore all of the rest of this and just focus on this part. So if I tell you you have 100 milliliters of a 5 molar calcium chloride solution, I want you to make 0.75 molar calcium chloride solution. How much water do you need to add? Is really the question that's being asked here. For this 0.75 molar calcium chloride solution, we don't know what volume that's going to be, so we can't calculate yet how many moles that's going to be. Remember, the dilution equation is really moles equals moles. So if you think about it like this, I've got this many moles. I'm going to use all of this. How many moles am I going to get of calcium chloride from this combination of volume and molarity? So what is molarity? Moles over liters. Come on, you should say it every time. Burn it into your mind. So this is going to be 5.0. Actually, let me write it over here. 5.00 moles per liter. And I have 100 milliliters of that. How many liters is 100 milliliters? 100 liters. So if I take my 0.100 liters, multiply it by 5 moles per liter, that'll tell me how many moles I'm starting with. And it's going to be 0.500 moles. So I'm starting with 0.500 moles. I want my solution to be 0.750 molar. So do I need to add, let's think about it like this. So 0.500 moles. If I added that to 1 liter, what would my concentration be? 0.5 molar. I want 0.75 molar. So should I add less or more water? So if I add more water, in this case, our amount of moles is fixed. Right? So we can't change the number of moles. We're just going to change how much water I add to it. Yeah, so we need to make this something less than 1 liter. I promise you the calculation for this is much easier than I'm making it right now, but I want you to think through it more conceptually than plugging things into the equation. Because the equation has a place, and it is only for dilutions. Okay, so we need less than 1 liter. How much less than 1 liter? And this is where we can use the fact that we want this concentration, because again, molarity is moles per liter. Thank you. So I want to know the liters, right? Because we don't know what this part is. So I'm starting with 0.500 moles, but I want, where do I want to write this? Shoot. So if I rewrite this as 0.750 moles per 1 liter, this is a conversion factor. If I know how many moles I'm starting with, I want to convert that into liters. How do I use this to convert to liters? Starting from, I want to convert this 0.5 moles into liters. Just flip the conversion factor. It's just like any other conversion factor, right? I have moles here, and I want to cancel that out, so I'll put these moles on the bottom, and then 1 liter on top. So 0.5 divided by 0.750 equals 0.666 repeating liters. So if I dilute this 100 mils of 5 molar to 0.666 liters, that should give me 0.75 molar. And we can confirm that by taking 0.500 moles and dividing it by 0.666 liters. Maybe I should have put one more 6 in there. Equals 0.75007, so it really rounds up, but molar. So the question was, to what volume should I dilute? The answer is 0.666, repeating liters. So the moles in has to equal the moles coming out. Most of the time, you're asking the question the other way. It's, I want to make a solution with this concentration. How much of the other solutions of whatever concentration do I need to add? Let me just, let's see, copy. Oh, duplicate, that's what I want. Okay. So if we start over and we just use the solution dilution equation, and it's M1, actually capital M, M1 V1 equals M2 V2. So my M1 and my V1 are going to be 5.00 molar and 100.0 milliliters. And the concentration that I want is 0.750 molar, and V2 is what I'm going to solve for. So 5 times 100 is going to be 500, and we did milliliters divided by moles, milliliters, and liters. That equals 0.750 molar times volume. So now I divide both sides by 0.75. Oh, I know. I know. All right, cool. Feedback received. Was not a great question to do it with. So the one thing to note here, I did this in milliliters, right? Molarity is moles per liter. The liters in the two molarities end up canceling out. So whatever volume unit you put in is the volume unit you get out. So if I'd started with liters for V1, I would get liters for V2. If I put in milliliters for V1, I get milliliters for V2. Okay. Solution stoichiometry then. I'm sure it'll still happen, but please never use dilution for stoichiometry. M1V1 equals M2V2 does not work for all stoichiometry problems. The tricky thing is that it will work sometimes. And when you're doing Alex, you're going to be very frustrated that it worked sometimes, but not all the time. And that's because we can have coefficients that matter. So before, we talked about basically grams, mass stoichiometry, right? If I start with grams of A, I can find the amount of A in moles, convert that to an amount of B in moles, and then we could get out grams on the other side, so we could do this, right? It's just, I'll write it in their terms, mass of A, and then we could get out over here, mass of B. It's the same basic process, we just got a new way to calculate moles. In some problems, we'll want you to end the question by calculating a molarity. So again, we're just using molarity to get from volume to moles, and then from moles to another volume. So what volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So how do we know that this is a stoichiometry problem, aside from the fact that it says that at the top of the slide? Two different solutions, two different compounds. So if there's two different compounds, another big hint is that there's a balanced chemical equation and that nitric acid and sodium carbonate are both part of this equation. So this is a stoichiometry problem. So what's the first step in any stoichiometry problem? The equation's already balanced. What do I need to convert from one species to another species in my balanced chemical equation? What units do I need? Moles. So the first step in any stoichiometry problem is to find moles, unless you're given moles. So we need to find moles of either HNO3, nitric acid, or of sodium carbonate. Which one of those can we calculate moles for? Yeah, so we have molarity for nitric acid, but we can't calculate moles of nitric acid unless we have volume. So sodium carbonate, we've got milliliters and we've got moles, or molarity, I should say. So we're going to start with sodium carbonate. But what are the units of molarity? Moles per liter. So this is 0.108 moles. Oops. Na2CO3 per 1 liter. I'll do it proper, and then I'll tell you there's a shortcut you can take on this. So we have to convert first then this milliliters into liters. Since we're short on time, I'm just going to do that. So that's liters of the Na2CO3 solution. So I find moles with my 0.108 moles of Na2CO3 per 1 liter. Now what? Mole ratio. So what's the mole ratio from sodium carbonate to nitric acid? 2 to 1, 1 to 2. It's 1 sodium carbonate, 2 nitric acids. And now I want to find, so that would give me the moles. And now I need to find the volume of nitric acid. So how do I go from moles to liters? Molarity, because molarity is moles per liter. Since we're starting with moles, so that means my 0.150 moles goes on the bottom. 1 liter on top. Great, that's crooked. So that's going to give it to me in liters, but we can convert that afterwards. So 0.51408 liters, sorry, 0.05, which is 51.4 milliliters of, okay, so here's the trick. Just like with, this only works if you're going from a volume to another volume in a stoichiometry problem. Just like in the other problems, moles cancels out with moles, liters cancels out with liters. It doesn't matter if I use liters or milliliters here, because whatever I put in here is the unit that I'll get out on this side. So I could have used, and this is why I hesitated at the beginning, because I could start with 35.7 milliliters, put that at the beginning, it'll come out as milliliters at the end, because all of the other units will cancel by the time I get there. So the only unit that'll be left is whatever I started with. Now it has to be a unit of volume. I'll have to try it later. I was just thinking, could it be ounces or gallons or something random? I think it could. So if you use M1V1, here, look. If I set this up as M1V1, so that's my M1. Oh, I told you could do this, so I'll just write this as 35.7 equals 0.150, and then calculate V2. What number's missing from that equation on the bottom? Mole ratio. If the mole ratio is 1 to 1, the result will be the same. If it's anything else, it's going to be different. You could. And then you're just doing stoichiometry anyway. If you can think it through and you don't get it wrong, it's fine by me. I do prefer when I can, as long as you write it out clearly enough that I understand what you did, can usually figure it out. But you could totally incorporate the factor in there somehow. All right.